Hello everybody. Today I will give you a presentation about implementation of robotics kinematics algorithm for industrial robot model using microcontrollers. And the author of this paper belongs to Karol Borowski and the Wodolewicz at Nation Poland. And I am Volngop Antoine. I will the one who take this presentation. Let's get started. For the table of content, we have introduction, methodology, result, and conclusion. For the first is introduction. What is a manipulator? Robotic manipulators play a significant role in modern industry. They are mechanical arms that, like human arms, are composed of members. In case of a human arm, such as a member is shoulder, forearm, hands, or a single finger. The members are connected by joints that allows them to change position. In mechanical, these joints are called hinges. It is impossible to imagine more prominent production line today without manipulators. They perform tasks that are too dangerous for humans, like working in a mechanical environment, and too difficult or even impossible to perform by humans, like handling weighty and bulky objects. They are also perfect for monotonous tasks, for which is not worth employing a man, and much more. Due to the very high capability of this machine, it's impossible that soon they will be developed in other industries closer to everyday life. Mechanical arms had also been used in surgeries in the beginning of first 21st century, and the primary object of this work is to develop a control system for a robot with 4 degrees of freedom, allow it to move in an X, Y, Z coordinate system. In addition to system layer, it is planned to design a hardware layer, a printed PCB. This is avoid the need of prototyping boards and cables, which is larger in projects become inconvenient to use and unreliable. The logic layer is decided to be implemented on microprocessor system. And we move to the methodology. First, we have control algorithm. Then we will move to description of the hardware we use in this project. Then we will describe the implementation of an embedded system for robot control. For the control algorithm, we have two methods used in this project. The first is analytical method based on the solving of the inverse kinematics equation of a robot. For the picture of both, we have a manipulator in a position at x and y in a xy coordinator, and we will determine x and y and move the manipulator to the x and y coordinate by solving the inverse kinematic equation, and we will find the Q1 and Q2. The second is Jacobi matrix. The Jacobi matrix defines the relationships between the joint velocities and the effector's resultant velocity, which mean here we have this is the velocity. This means the derivation of x, y, and z. A Jacobian algorithm is chosen to solve the inverse kinematic test about two tasks we just described before. It defining the relationship between the velocity of the effector and the velocity of the individual joy. Why? Each of compare methods has its advantages and disadvantages. The analytical method has a very high accuracy paper at expensive computation speed. The algorithm in this paper was implemented on a microprocessor with limited computing power, so the execution time for the kinematic calculations was an important issue. The processor has to fast enough to execute the inverse kinematic algorithm, drive the full model, handle the communication with user, and even send data to the external computer in a reasonable time frame. In this respect, the inverse Jacobi matrix is a better algorithm, so that we will choose the Jacobi algorithm to use in this project. For the next movie description of the hardware, the robot model we use in this project has 3 degrees of freedom with additional freedom at with a additional degree at the end of n effector with spin freedom. The hardware each choice had a minimum angle and maximum angle that is display of Cartesian coordinate system over the effector can move. Uh, It has old motors and gears which were replaced with a new one. The robot models had 3 degrees of freedom as I said, defining the robot's position in X, Y, Z space. The first one over here is responsible for the rotation around the vertical axis, and the next two control the rotation around the horizontal axis. In addition, the robot has a fourth, which means the additional degree of freedom, is responsible for effector rotation. This is also possible for connect a motor that controls the landing of the gripper, but this option was not considered on this work. And the hardware layer interface board is responsible for collecting all the signal from the external components and transferring them to the second program board, which is an overlay to the STM32 Nucleo. And the main controller is the STM32 Nucleo 64 kit with the STM32 F401RE Cortex M4 84MX processor that will be used as the CPU or the main controller of this robot, and for the display as a human interface we will use the STM32 F769i Discovery Runtime Kit with the STM32 F769 NH6 microcontroller. And the implementation of an embedded system for robot control. The program we will use in this embedded system will be the C language, and combined with them is the STM32Cube ADA environment. The C language in this environment is that and the free RTOS, and for that we will use the graphical interface that was implemented on the STM32F7 Discovery Development Kit using TouchGFS environment. For the result of the experiment, according to the work, the robot can be controlled in three ways. After implementation of the algorithm, their quality was tested. The test was performed using the manipulator. The system sent the necessary to the MATLAB through the UART interface, which was then presented as a graph depending on the number of samples T divided by Ts, where the Ts is the sampling period of equals to 10 microseconds. The different trajectory adjusts for different effector resolution velocity. A trajectory consisting of 3 points is tested for effector velocity of 1 centimeter per second, 2 centimeter per second, and 5 centimeter per second. And after testing, the best result for a given trajectory was achieved at 2.5 centimeter per second. So, arrows at state are larger at low speed and smaller for higher speed. In contrast, the segment between the start and point 1 were mainly vertical, so the adjustment on the segment is more accurate for a lower effector velocity. And after this test, we will give a conclusion. The accuracy of manipulator control is dependent on the set effector velocity. It cannot be too low because then the accuracy of joint velocity control decrease. If the speed were too high for some trajectory, there is a risk that requires speed of a slower joint not reachable by it. And my presentation